Hello everyone and welcome. My name is Weichen Gan and I am an application engineer with Bettersize Instruments Limited. Today, I'm excited to introduce our innovative submersible particle size analyzer, the DeepSizer 300. To give you a comprehensive overview, we will cover 5 main sections. We will start with the fundamental concepts behind our technology, then move to the optical setup and the unique technologies of DeepSizer 300. We will also cover the control modes and software and finish with some real-world application cases. Let's begin with the fundamental concepts. We will explore the key results the DeepSizer 300 provides and the core technology it uses for the measurement. The DeepSizer 300 delivers two critical results: particle size distribution (PSD) and suspended sediment concentration (SSC). PSD measures the amount of different-sized particles, which is vital for understanding how sediment moves and where it settles. This data helps researchers predict river channel changes and check pollutants. SSC measures the dry weight of that sediment, which dictates whether a river is building up or eroding its bed, and it is essential for managing reservoir capacity and assessing environmental impact. To reiterate on particle size distribution, understanding both particle size and the sizing process of sediments is crucial. We all know that PSD plays an important role in various subtopics in the field of hydrology, so an accurate PSD test is particularly important. But how do you get accurate PSD results? Let's see. Many technologies exist for particle sizing, each with its own effective range. As this chart illustrates, laser diffraction, the technology used in the DeepSizer 300, covers a broad spectrum from microns to millimeters, making it ideal for analyzing the wide variety of suspended sediments found in nature. The DeepSizer 300 measures particle size using light diffraction. When incident light hits a particle, it scatters, creating a pattern that depends on the particle size. As you can see, large particles produce a more concentrated pattern, while smaller particles scatter the light more widely. Our instrument's detectors capture these patterns to determine the size distribution. The process is straightforward. First, the instrument captures the scattering spectrum from the particles. Then, an applicable theoretical model, like Fraunhofer or mean theory, is applied to predict how particles of different sizes but the same material scatter or diffract the light. Next, a mathematical conversion, which divides the complex scattering pattern into patterns of large and small particles. The way how particle patterns made up a total pattern is the final particle size distribution. So, what advantages does a laser diffraction analyzer offer? It provides reliable data that is widely accepted in the scientific community and covers the entire common range of suspended sediment sizes. The measurements are fast and highly repeatable, ensuring you get stable, trustworthy data every time. Let's turn to measuring concentration. To be specific, the Suspended Sediment Concentration, or SSC. SSC is a critical indicator that dictates whether a river is building up its bed through deposition or cutting down through erosion. SSC is so important, but it keeps changing every second as a natural water body flows. That calls for a test method that balances test efficiency and test accuracy. So, how can we measure concentration in real time? We use a principle called light extinction, which is based on the Beer-Lambert law. The concept is simple. The more particles there are in the water, the more light gets blocked. The instrument measures the initial laser intensity I0 and the final intensity I after it passes through the sediment. The key advantage here is that our system already knows the particle size from the diffraction measurement. By combining the particle size with how much light was lost, we can directly calculate the sediment's volume concentration, giving you an accurate real-time SSC value. Now, let's take a look back at how SSC is measured. There are two primary methods to consider. On our right is the traditional gravimetric method, a direct measurement where a water sample is dried or filtered and the sediment is weighted. Its main advantages are its accuracy and its ability to provide calibration data. On our left is the light extinction method, which is the technology that DeepSizer 300 employs. It combines light absorption with particle size data to calculate the volumetric concentration. The advantages here are significant. It allows for in-situ real-time monitoring, which reduces labor and dramatically improves safety. Now that we have covered the fundamental concepts of how the DeepSizer 300 measures particle size and concentration, let's move on to Part 2, the system setup. In this section, we will take a closer look at the instrument itself. We will start with the detailed specifications and the core optical design, and then I will show why DeepSizer 300 is a perfect choice for in-situ monitoring of suspended sediments. Here are the core specifications of the DeepSizer 300. As we discussed, it measures particle size distribution (PSD), suspended sediment concentration (SSC). Also, the water depth, temperature, and optionally conductivity can be measured. The PSD measurement range is from 0.1 to 2000 microns, and the SSA range is from 0.001 up to 100 grams per liter, covering a wide range of water body conditions. It's rated to a depth of 300 meters and has an IP68 waterproof rating. The optical system uses a high-powered 10 mW laser and 80 detectors to achieve its wide measurement angle. In the sedimentation analysis field, the traditional laboratory analysis method is both time-consuming and labor-intensive, often taking hours or days. It requires careful on-site sampling, which carries risk and can have issues with sample representativeness. The DeepSizer 300 provides an in-situ real-time solution. It offers customizable test frequency, requires no sampling or sample preparation, and eliminates the dangers of working in the water, all while ensuring representative data. Let's look closer at the optical design. The system features a high-powered 10 mW laser and a set of 80 detectors that cover a detection angle from 0.016 to 42 degrees. We utilize a Fourier design and an adaptive measurement zone width, allowing for accurate and simultaneous measurement of both PSD and SSC. We chose a Fourier design for a specific reason. While a standard inverse Fourier design can offer high accuracy on very small particles, as small as submicron particles, it requires particles to be on the same plane, which means they need to be arranged as a monolayer. In a natural water body, it is almost impossible for particles to be on the same plane. That's where Fourier design comes in, as it does not require particles to be in a monolayer, making it perfectly suited for in-situ sediment analysis. The advantages of this optical setup are clear. It provides a stable system that adapts to different water conditions, is highly sensitive and accurate across the entire measurement range, and is capable for capturing everything from large millimeter-sized sands down to fine micron-sized clays. The accuracy of our system is validated through rigorous testing. Here, you can see results from tests on certified reference materials ranging from 400 nanometers to coarse sands and very coarse sands, the VC. The key takeaway is the relative standard deviation, or RSD, which is consistently below 1%. This demonstrates the excellent accuracy and repeatability of the DeepSizer 300. Furthermore, when compared to our high-end desktop instrument, the Bettersize S3, the results show strong agreement. We see the same high accuracy for concentration measurements. This graph shows a direct comparison between the DeepSizer 300 and the gravimetric method. The results are highly consistent with an R-squared value of 0.9974, indicating an almost perfect linear correlation. The second graph further confirms this, showing the instrument's data closely tracking the dry method results across the numerous tests. We have covered the optical system. Let's move on to the unique patented technologies that truly set the DeepSizer 300 apart from any other instrument on the market. To perform an accurate in-situ test, you face a real challenge: background signals. The optical signal collected by the detector isn't just the scattered light from the sediments. It also includes light deviation from the water itself, ambient light, and electronic noise. In the lab, you can perform a background test with pure water, but in the river or ocean, that's impossible. These background signals must be excluded to get a pure particle signal, and that's a problem our differential pass technology is designed to solve. So, what is differential pass technology? It's an innovative solution achieved with a movable chamber inside the DeepSizer 300. During the test, this chamber moves to change the width of the measurement zone, creating two differential optical pass lenses. By capturing signals at both pass lenses, the instrument can isolate the true signal from the particles. This is how it revolutionizes the measurement. The system captures one signal at the first position and a second signal at the other. Because the background signal is consistent in our Fourier design, a simple subtraction cancels it out completely. This leaves us with a pure scatter signal from only the particles in the differentiated volume, allowing us to get a clean result without ever needing a background test. Next, we will discuss another key innovation, our adaptive pass technology. Our measurement principle assumes that the light is scattered only once by each particle. However, if the water is very turbid and the particle concentration is high, multiple scattering can occur, which leads to inaccurate results. To solve this, the DeepSizer 300 automatically shortens the width of the test area in high concentration water, reducing the probability of multiple scattering and ensuring accuracy of both PSD and SSC tests. How does this benefit your measurements? This technology allows the instrument to adapt to complex and challenging environments, providing more accurate results across a much wider range of sediment concentrations. No manual adjustment is ever needed, which means it can provide continuous, reliable testing even during the drastic changes in water conditions seen during a flood season. Of course, operating deep underwater presents its own challenges. At a certain depth, the external hydraulic pressure can be so great that it prevents the instrument's chamber from moving, which would disable the differential and adaptive pass technologies. We needed to engineer a solution to overcome this. Our solution is the self-balancing hydraulic pressure compensation system. We designed a rigid synchronous frame that connects the two freely moving ends of the measurement chamber. Now, instead of pushing one window against the immense water pressure, the motor drives the entire synchronized structure as a single unit. This completely neutralizes the effect of water pressure on the system movement. Another challenge in any long-term deployment is fouling. When sediment particles, algae, or microorganisms attach to the optical windows, they contaminate the test windows and affect the accuracy of the results. To solve this, the system automatically activates a cleaning function using a brush to wipe the test windows and restore normal operation, keeping the optics clear for accurate detection. Finally, for extremely turbid conditions, we have a final layer of protection for your data. Very high obscuration can still lead to some multiple scattering, which can cause the particle size results to be underestimated. To adjust this, the DeepSizer 300 software includes a specially developed multiple scattering correlation algorithm that effectively corrects for this issue, ensuring precise results even at high concentrations. Now that we have covered the hardware and unique technologies of DeepSizer 300, let's move on to the next sections where we will discuss the control modes and software that drive the instrument. The entire testing process of DeepSizer 300 is designed to be fully automatic, delivering a complete in-situ analysis of SSC and PSD with minimal effort. The workflow is a simple pre-programmed sequence. It begins when DeepSizer 300 detects that it has reached a preset water depth. Once in position, it automatically starts the measurement process. First, it performs an auto-clean of the test windows, followed by an auto-alignment of the optical system to ensure precision. Then, based on the water stability, it makes an automatic adjustment to the optical path. Only after all these system checks are complete does it measure the particle size distribution and sediment concentration. Finally, the results are automatically saved and can be printed or exported. The DeepSizer 300 is incredibly versatile. It can be deployed in a variety of environments, whether it's from a cableway over a river, installed on a bearing pile in a lake, or operated from hydrological vessels in both rivers and oceans. The DeepSizer 300 offers three flexible control and data transmission modes. The first one is wired transmission. This method uses a direct RS-485 connection between the instrument and the computer, allowing for full control and real-time monitoring of all signals. This mode is ideal for situations where you have a stable power supply and a suitable working environment for computer operation, for example, working from a riverbank station or vessel. Second is wireless transmission with a 4G module. This connects the instrument to your computer over the wireless network, enabling operators to control the instrument remotely from the comfort of the office. This is perfect for fixed installations where a power supply is available and the site has 4G network coverage. Finally, we have offline transmission. In this mode, you can pre-configure the instrument's perimeter before deployment. The internal CPU and battery allow it to operate without external power supply and control for outdoor monitoring. Data is stored on an internal SD card and can be retrieved later. This mode is ideal for remote locations where no on-site power supply is available. We have covered the instrument's operation. Let's look at some real-world application cases to see how the DeepSizer 300 performs in the field. Our first case study takes us to the Yangtze River estuary, where we tackled a significant challenge, tracking sediment concentration changes during flood peaks. Traditional sampling methods are often too slow, meaning the most critical moments of a flood event are missed entirely. Our solution was to deploy the DeepSizer 300 and have it transmit data every 5 minutes using a 4G module, ensuring a continuous, high-frequency data stream. The results were truly revealing. DeepSizer 300 successfully detected multiple sediment concentration peaks that exceeded 20 kilograms per cubic meter, and traditionally daily or even hourly sampling would have completely missed those surges. This provides immense value. For the first time, researchers and managers can get real-time monitoring of sediment trends during the most dynamic events without any risk. This capability is directly applicable for most responsive flood control scheduling, effective estuary management, and deeper scientific research. Our second case from Taihu Lake was designed to provide an intelligent solution to replace traditional sampling measurement methods. The challenges with conventional methods are twofold. They are time-consuming and cannot simultaneously provide both SSC and PSD. We installed the DeepSizer 300 on the buoy to measure both perimeters automatically and transmit the data via 4G. Let's look at the results, starting with concentration. This graph directly compares the data from the DeepSizer 300, the blue line, with the results from the traditional gravimetric method, the orange line. As you can clearly see, the data from our instrument tracks the direct measurement method with remarkable consistency across a wide range of concentrations. This demonstrates that our new efficient method can seamlessly replace the traditional approach without sacrificing accuracy. Beyond just concentration, the DeepSizer 300, as we know, provides continuous particle size data. This graph shows the D10, D50, and D90 values over the course of 65 measurements. The relative stability in the particle sizes, especially in the D50 or medium size, provides valuable insights. It can help researchers understand the sources of the sediment and how it's being transported within the lake ecosystem, information that was previously unavailable with this level of detail. The value provided in this case is clear. We have a solution that is not only accurate and operates in real time without manual sampling, but it also enriches the data significantly. Our final case highlights the challenge of rapid sediment measurement in complex river environments using a cableway. The goal here was to quickly obtain both SSC and PSD data in the location where deploying other sampling or testing equipment would be difficult or dangerous. The solution was to mount the DeepSizer 300 on a leadway, positioning it precisely with the cableway, and begin automatic measurements with data transmitted wirelessly for analysis. Looking at the data, on the left, you can see the sediment concentration trend over the course of about 45 measurements. It shows an initial high concentration that drops and then stabilizes, providing a clear picture of the event. On the right, we have the particle size trend. While the D10 and D50 values remain relatively consistent, you will notice several dramatic spikes in the D90 value, which represents the largest particles. This indicates that occasional bursts of much coarser material or organic debris were passing through the measurement zone, providing a nuanced view of the sediment transport that a simple concentration value would miss. A little about us. Founded in 1995, Bettersize is China's leading particle sizing instrument manufacturer with 30 years in the business. Our instruments and services are trusted by tens of thousands of customers worldwide, from leading universities to global enterprises. At Bettersize, our mission is to provide best-in-class instruments, comprehensive solutions, and exceptional customer service. We are dedicated to assisting scientists, researchers, and engineers worldwide in understanding material properties, facilitating research, improving product efficiency, and beyond. Throughout this presentation, we have discussed the significant challenges of traditional sediment monitoring. It's slow, labor-intensive, and often misses the most critical events. We introduced the DeepSizer 300 as a robust, in-situ solution that revolutionizes this process by providing real-time data on both particle size distribution and suspended sediment concentration. We have seen how its advanced design ensures accuracy in the complex conditions of natural water bodies, and we have explored the unique patented technologies that makes it possible. As our application cases have shown, this result is a system that not only replaces traditional methods, but provides richer, more continuous, and more valuable data with improved safety and efficiency. Bettersize is proud to offer this solution to help advance scientific research and environmental management. Thank you for your time. For more information, please visit our website at bettersizeinstruments.com.